Today's lecture will focus on the system properties of causality and memoryless. You should be reviewing Chapter 4 of the course notes for supplemental instruction on this content. The objective of today's lecture is to define the system properties causality and memoryless and to determine if a system is causal and or memoryless. A system is causal if for any time t1, the output response y of t1 resulting from the input x of t does not depend on values of the input x of t for t greater than t1. In other words, in a causal system, it is not possible to get an output before an input is applied to the system, assuming no initial energy. An example of a system that would not be causal would be some type of anti-skip CD system where it actually anticipates the next value so that if you're using it and you bump something, you don't hear the bump in the music. A system that is non-causal, if it is not causal, is a system where the output only depends on present and past values of the input. A system is said to be memoryless if for any time t1 the value of the output at time t1 depends only on the value of the input at time t1. So a memoryless system is an example of a causal system. However, a system that is not memoryless is said to have memory. In a memoryless system, the output only depends on present values of the input. Let's do an example. Determine if the following system is causal and or memoryless. Probably the easiest way to check this system is just to use numbers. So let's say I want the output at time y of 2. So to get the output at time y of 2, then I have to find the input at the time x of negative 2. Since the output at any current time always depends on the past value of that time, this system is said to have memory. And because it depends on past values of the input, it is also said to be causal. The only way that this system would be memoryless is if the output at time t only depended upon the input at time t. But because it depends on these past values, it is causal and it does have memory. All right, let's try another example. Determine if the following system is causal and or memoryless. Y of t is equal to the integral from t naught to t 2x of lambda minus 1 d lambda. So the way to think about this is that if I want the output at time t, then I have to find the input at x of t naught minus 1 to x of t minus 1. So since the output at time t does depend on past values of t, you would say that this system is causal, but because it depends on past values of x, it does have memory, so it's not memoryless. So you can either put has memory or not memoryless. So now let's look at the same circuit that we analyzed in the prior lecture, but now we're not going to assume that it has zero initial conditions. Determine if the following RL circuit is causal and or memoryless. Recall from before that we found that K was equal to negative 1 over RA and tau was equal to L times RA plus RB over RA times RB, and the output Y of t is equal to e to the negative t minus t naught over tau y of t naught plus the integral from k over tau plus the integral from t naught to t e to the negative t minus lambda over tau x of lambda d lambda. So what you should see here is that the output y of t only depends on x of lambda from x of t naught to x of t. Since this includes past values from t naught up to t, you would say that this system is causal and that it also has memory. So far we have seen 3 examples of systems that were causal and have memory, but let's explore some more. So now let's complete the following table. For each of the following mathematical descriptions of a system, determine if it is linear, time invariant, causal, and memoryless, and complete the table. For causal and memoryless, you can typically look at the system description and determine that. However, there should be some type of formal technique to determine if a system is linear and or time invariant by using the signal flow graphs that we discussed in the prior lecture. We will do each of these on a separate page so that you can clearly see how we could arrive at the answer. The first system is y of t equals x of t plus b. As you can see here, for the output at time t, it only depends upon x at time t. So the system is definitely causal. And because it does not depend on past values of x of t, it is also definitely memoryless. Now, based upon the rule we had for homogeneous, we can immediately see that this is not going to be linear because when the input is 0, the output is b. So it is nonlinear. However, to show the formal process, I will do the signal flow graph. So for example, if the input is alpha x1 of t plus alpha x2 of t, and I send that through my function, I know that my output is going to be alpha x1 of t plus alpha x2 of t plus b, and that's z1 of t. z2 of t is equal to alpha 1 y1 of t plus alpha 2 y2 of t. So this equals alpha 1 times the quantity x1 of t plus b plus alpha 2 times the quantity x2 of t plus b. Doing a little bit of rearranging, I will have alpha 1 x1 of t plus alpha 2 x2 of t plus alpha 1 plus alpha 2 times b. So as I just said, because we have this term b, z1 of t is not going to be equal to z2 of t. So this system is nonlinear. So this is no. Now let's check time invariance. For time invariance, when the input is x of t minus t naught, and you send that through our function, the output is x of t minus t naught plus b, and that's z1 of t. Y of t minus t naught is going to be z2. So if you take the output x of t plus b and delay it by t naught, you have x of t minus t naught plus b. So in this case, z1 of t equals z2 of t. So we do have a time invariant system. So the answer for that part is yes. Okay, let's try another example. If the system description is y of t equals x squared of t, that means that the function states that whenever you have an input x of t and it goes through the function, you square the input. So if our input was alpha 1 x1 of t plus alpha 2 x2 of t, and we send it through our function, then on the output we're going to have alpha 1 x1 of t plus alpha 2 x2 of t, quantity squared, which is alpha 1 squared x1 squared of t plus 2 alpha 1 alpha 2 x1 of t x2 of t plus alpha 2 squared x2 squared of t, and that equals z1 of t. Now z2 of t will equal alpha 1 y1 of t plus alpha 2 y2 of t, which equals alpha 1 times x1 squared of t plus alpha 2 x2 squared of t. So only the beginning term and the last term are the same. This one and this one compared to this one. But because of that middle term, it keeps them from being equal. So since z1 of t is not equal to z2 of t, we say that we have a nonlinear system. So now let's check for time invariance. If my input is x of t minus t naught, and it goes through my function, then my output is x squared of t minus t naught, and that's z1 of t. If I have y of t minus t naught, I delay my output due to the input x of t. This equals z2 of t again. This equals x squared of t minus t naught. So since z1 of t equals z2 of t, we say that we have a time invariant system. So no, the system is not linear, and yes, it's time invariant. And once again, the output at time t only depends upon the input at time t, so we do have a causal system, and it's only dependent upon the present time, so it's also memoryless. So now let's look at the system 1 over x of t. Once again, the output at time t only depends upon the input at time t, so we definitely have a causal system. And because it only depends upon present values of x, it is also memoryless. So now let's look at our signal flow graph to determine if it's a linear system. The function states that when input is x of t, the output is the reciprocal or the inverse of the input. So if the input is alpha 1, x1 of t, plus alpha 2, x2 of t, and we send it through our function, h, then the output is 1 over the quantity, alpha 1, x1 of t, plus alpha 2, x2 of t, and this equals z1 of t. But now let's check the second row of the signal flow graph, alpha 1, y1 of t, plus alpha 2, y2 of t. This means take the output due to x and multiply by alpha 1. So it's going to be alpha 1 times 1 over x1 of t plus alpha 2 times 1 over x2 of t. And it should be immediately clear that z1 of t does not equal to z2 of t. So this is a nonlinear system. Okay, now let's check time invariance. If I have an input, x of t minus t naught, and I send it through my function, then the output is 1 over x of t minus t naught. And this is z1 of t. z2 of t is y of t minus t naught. So I take my output due to x of t and delay it, and this would give me 1 over x of t minus t naught. And here we see that z1 of t does equal to z2 of t. So this is a time invariant system. So we put yes. So now let's try y of t equals the absolute value of x of t. Once again, the output at time t only depends upon the input at time t, so this is a causal and memoryless system. And now let's use the signal flow graph to check linearity. If my input is alpha 1, x1 of t, plus alpha 2, x2 of t, and I send it through my function, then the output is the absolute value of the quantity x1, x1 of t, plus alpha 2, x2 of t. And this is z1 of t. z2 of t is going to equal alpha 1, y1 of t, plus alpha 2, y2 of t. So whatever the input is, the output is the absolute value of that. So this is going to equal alpha 1 times the absolute value of x1 of t, plus alpha 2 times the absolute value of x2 of t. You should be able to immediately see that these are not going to be the same, because depending upon the values in this first, you won't get the same numeric number for both. So z1 of t does not equal to z2 of t. So once again, we have another nonlinear system. And now let's check time invariance. So for time invariance, if the input is x of t minus t naught, and we send that through our system, the output is the absolute value of x of t minus t naught. And that's z1 of t. z2 of t is y of t minus t naught, which means you take your output and you delay it, and this also gives you the absolute value of x of t minus t naught. So in this case, z1 of t does equal z2 of t, so we do have a time invariant system, so that's going to be yes. Our next system is y of t equals the sine of x of t. Once again, the output at time t only depends upon the input at time t, so we have a causal and a memoryless system. Now let's check linearity. If the input is alpha 1, x1 of t, plus alpha 2, x2 of t, and we send this through our function, then the output should be the sine of the input. So this is going to be the sine of the quantity alpha 1, x1 of t, plus alpha 2, x2 of t, which is z1 of t. z2 of t will equal alpha 1, y1 of t, plus alpha 2, y2 of t. So alpha 1 times the output due to x1 is alpha 1 times the sine of x1 of t, plus alpha 2 times the output due to x2 is alpha 2 times the sine of x2 of t. And it should be immediately clear that z1 of t is not equal to z2 of t, so this is once again a nonlinear system. So far we've seen several nonlinear systems, but we'll see an example that is linear momentarily. And now let's do time invariance. If the input is x of t minus t naught, and I send that through my function, the output should be the sine of the input. So this is the sine of x of t minus t naught, and that's z1 of t. And z2 of t should be equal to y of t minus t naught. So you take the output due to x of t and delay it by t naught, and you get sine of x of t minus t naught. So once again, z1 of t equals z2 of t. So this is a time invariant system. So not linear, but it is time invariant. So let's look at the system y of t equals alpha of t x of t. Once again, the output at time t only depends upon the input at time t. So we have a causal system that is also memoryless. And now let's use the signal flow graph in order to determine if this system is linear. If my input is alpha 1, x1 of t, plus alpha 2, x2 of t, and I send it through my function, what the function does is multiplies the input by alpha of t. So I have alpha of t times the quantity alpha 1, x1 of t, plus alpha 2, x2 of t, and this equals z1 of t. z2 of t is equal to alpha 1, y1 of t, plus alpha 2, y2 of t. So this equals alpha 1 times the output due to x1 of t, so that's alpha of t, x1 of t, plus alpha 2 times the output due to x2 of t, which is alpha t times x2 of t. And with a little bit of rearranging, you should be able to note that these are equivalent. So z1 of t does equal to z2 of t. So we finally do have a linear system. So that's yes. And now let's check time invariance. First thing we're going to do is input x of t minus t naught, and when I send that through my function, what it does is it takes the input and multiplies it by alpha of t. So I'm going to have alpha of t times x of t minus t naught, and that's z1 of t. z2 of t is going to be the output due to x of t, delayed by t naught. So that's y of t minus t naught. So in this case, you find every t in the output and delay it. So that's alpha of t minus t naught, x of t minus t naught. So you can immediately see that we have a problem here. And the problem here is that z1 has alpha of t and z2 has alpha of t minus t naught. And because those two values are different, z1 of t is not equal to z2 of t. So I do not have a time invariant system, or it's not time invariant. So this is no. All right, let's look at the next system, x of t over 2. This time, in order to check that the system is causal, I'm going to put in some numbers. If I put in y of 1 as the output, then I know this has to be equal to an input of x of 1/2. Or if the output is at time 2, then that is the input at time 1. So since the input depends upon past values of x, we will say that this is a causal system. However, since it looks at past values, not just the present value, it's not memoryless. So now let's check linearity. So if I have an input, alpha 1, x1 of t, plus alpha 2, x2 of t, and I send that through my function, then the output is alpha 1, x1 of t over 2, plus alpha 2, x2 of t over 2. And this is z1 of t. z2 of t is equal to alpha 1, y1 of t, plus alpha 2, y2 of t. So alpha 1 times the output due to x1 is alpha 1 times x1 of t over 2, plus alpha 2 times the output due to x2 is alpha 2 times x2 of t over 2. And we can quickly see that z1 of t equals z2 of t. So this is indeed a linear system. So now let's check time invariance. If the input is x of t minus t naught, and I send this through my system, what this means is that I should take my input and delay it by t naught on the output. So this is x of t over 2 minus t naught. And this is z1 of t. z2 of t is equal to y of t minus t naught. So I take my output due to x of t and delay it by t naught. And what this means is everywhere I find a t, replace it with t minus t naught. And this gives me x of t minus t naught over 2. And you can quickly see that z1 of t is not equal to z2 of t. So this is not time invariant. So now that we've done several examples of this, there's some that we can immediately look at and determine whether it's linear, time invariant, causal, or memoryless. We can immediately see that if y of t is equal to x of t plus 1, this is going to be a linear system. There's no initial conditions. And there's no squares or absolute values or anything, or signs or anything like that that would make it nonlinear. And we immediately see that if we delay the input, the output will be delayed. So we can immediately see that this is also time invariant. However, because the value at time t depends upon the input at t plus 1, it's not causal because it depends on a future value. And because it depends on a future value, it's also not memoryless. If you put in numbers to see this, you would see that at y of 0, this depends upon x at time 1. So that's a future value of x. Similarly to the last problem, what if y of t is equal to x of t minus 1? You can immediately see that this is linear, and it is time invariant. And let's say the output at time 1 depends upon x of 0. So you can see that it depends on a past value of the input, so it is causal, but because it depends on a past value, it is not memoryless. Okay, let's look at the system y of t equals x of 1 minus t over 2. You can quickly verify that this is a linear system. But let's look at causality and memory first. Let's say we want the output at time 0. The output at time 0 is x of 1, which is a future value. So because that's a future value, it's not causal and it's not memoryless. Although, if you wanted it at, let's say, y of 1, then this would be x of 1/2. So since depending upon what the output is, you either have a past, present, or future value, it's not memoryless and it's not causal. Now how about if we check for time invariant? If the input is x of t minus t naught, and I send that through the function, then the output is x of 1 minus t over 2 delayed by t naught, and this is z1 of t. z2 of t is equal to y of t minus t naught. So now if I take the output due to x of t and delay it, I'm going to replace every t with t minus t naught, so I'm going to have x of 1 minus the quantity t minus t naught over 2. And you can quickly see that z1 of t is not equal to z2 of t. So this is not time invariant. Okay, here's the final example of today's lecture. Once again, since we just have a constant multiplying x of t, this is going to be a linear system. Now, for y of t, the output at time t depends upon the input at time t. So we do have a causal system and we do have a memoryless system. But now let's check time invariant. If the input is x of t minus t naught, and we send that through our function, then the output is e to the t plus 1 x of t minus t naught, and this is z1 of t. z2 of t is equal to y of t minus t naught, which means you delay the output due to x of t by t naught. So every value of t becomes t minus t naught. So this is e to the t minus t naught plus 1 x of t minus t naught. So now what keeps z1 and z2 from being equal is the exponent on e. So because z1 of t is not equal to z2 of t, this is not time invariant. And this concludes today's lecture on system properties, including linearity, time invariance, causality, and memory.